This video will be on section 6.1, area between two curves. I guess I should write 2 in here to be more specific. But what we'll do is we'll first visualize looking at the area between two curves, and then we'll do a few problems computing it. What we will see, because I know you can already kind of look down here and ask that that's a lot of words. What we will see is that we've really been doing the area between two curves the entire time we've been doing definite integrals. The way we were thinking about it, though, is one of the curves was the x-axis, which is y equals 0. So all we're going to do is have to make a minor adjustment, and then we will figure out how it's pretty much the same thing. All right, so what we'll do, we will begin this section by recalling the definite integral and what it tells us. If f is a continuous function from a to b, then the definite integral represents the quote-unquote area between the graph of f of x and the x-axis. And then we also saw examples back when we started doing these, that area can be negative, this quote-unquote area can be negative if it's below the x-axis. So for this specific example, if we write the x-axis as the equation equals 0, then we have the area between y equals f of x and y equals 0 is one of these two. So if the f of x is above the x-axis, that means when we integrated it, we get a positive number. So this is really just our normal integral. And when we subtract 0 off, it doesn't do anything. That's why we have this minus 0. Now, when f of x is below the x-axis, when we want the actual area between, we want the area to be positive. So that's the key difference between the words area and the words definite integral. The definite integral is like an area, but area still must be positive. So when our graph was below the x-axis, our definite integral was negative. To make it positive, what we would do is we would put a negative sign in front of it. But I kind of write it in this weird way of 0 minus f of x, and I'll explain that in a second. So when this is below the x-axis, we multiply by -1 to make it positive, right? Because we want the area to actually be positive. Now, I think comparing this to our old stuff can be a little confusing. It's going to be more easy when I explain it in words. So this next one just says this is how we can make sure the area is positive, no matter what. Is if we want to find the area between two curves, y equals f of x and y equals g of x, from x equals a to b, we integrate from a to b, f of x minus g of x, but the absolute values make it so it's positive. Because we want area to be positive. But we haven't talked about integrating with an absolute value, and really it's not that nice to deal with, because you have to break apart your integrals and make multiple integrals and everything else. So there's an easier way to think about this, and this is what I'm really going to use. Is if you can know which curve is on the top and which is on the bottom, this is the one we will use. And I think it's just better in words than in formula anyway. We integrate from a to b, and the inside is the top minus the bottom. Right, so whichever function is on the top, you'll be given two equations. Which one's on the top, we'll figure it out. That one will go in front. The bottom function will go in the back. Right, but just to kind of reinforce this visualization here, there's one problem in the homework that'll look something like this. And I guess it got really blurry when I tried to transfer it. So the numbers here are a and b. This is the x-axis and the y-axis, like normal, and then the equation here, it says y equals h of x. And it says explain why the integral from a to b of h of x does not represent the area between the graph of y equals h of x and the x-axis from x equals a to x equals b. Well, this is a straightforward answer because area must be positive. But when you integrate a function below the x-axis, the definite integral is negative. Right, so that's the main difference here between doing the definite integral and finding the area is if your function is below the x-axis, you're getting the definite integral. You need to multiply it by -1 to get the area, your final answer. Okay. Right, so that's the main thing here. And that it basically boils down to the fact that when we find the area between two curves, we're going to do the top minus the bottom. But the two curves here we're comparing are y equals j sub x and the x-axis. And the x-axis happens to be the one on top. So it'd really be 0 minus h of x, which is just negative h of x to integrate. Right? But once again, that's really what this area between two curves comes from. I think it's best now, let's go ahead and work some problems. So number 1 here, the directions for these two problems. Find the area bounded by the graphs of the indicated equations over the given interval. So what will happen in all these problems, at minimum, you will be given two functions. What we need to do is figure out which one is on top and which one is on bottom. But you do have to be careful because you only care which one's on top or on bottom on the given interval. Right, we don't care at what happens at x equals 100, which one's on top and bottom, because we only care about what's happening between -3 and 0. All right, so the easiest way to do this, you don't even have to use a calculator. Just plug in a number between. Don't plug in the endpoint, so I'm not going to plug in -3 or 0. Plug in an x value inside the interval to each. What's going to come out is a y value. The bigger y value corresponds to the top one. Right, so I'm just going to plug in -1. But as a general rule of thumb, don't plug in the endpoints. So I'm not going to plug in -3 or 0 like I mentioned. I'm going to plug in -1. For the first one, we got y equals -1 squared minus 16. -1 squared is 1 minus 16 is -15. And the second one, that's just the equation y equals 0. So no matter what we plug in, we get 0. And we can see that comparing these two numbers, 0 is bigger. So this is the top. -15 is smaller, so that's the bottom. Right, so the way we set up our integral to find the area, we integrate, these are the bounds, so, oops, a is the smaller number. A is -3 and b is 0. We integrate from 0. I keep doing that. The 0 is messing me up. We integrate from -3 to 0. We do the top, which is the 0, minus the bottom, since we have two terms here, make sure you put parentheses for what you're subtracting. X squared minus 16 dx. But once you have this set up, you can almost forget about the problem now and just do this. Figure out this integral. This is exactly the kind of problems we were doing before. Okay. So when we simplify this, what I'm going to do, what I always recommend is simplifying the inside first. It doesn't matter if there is just a zero here. It's important just to simplify the inside first. It makes integrating much easier. So the zero is nothing. Distribute the negative sign through, and we get negative x squared plus 16 dx. Right, but we can integrate this. We can integrate each part. Pretty straightforward. The integral of negative x squared is negative x cubed over 3. The integral of 16 is 16x. And once again, that zero tripping me up. I'm so used to putting 0 on the bottom. But we have negative 3 on the bottom and 0 on the top. And now we plug in top minus bottom, just like from before. We plug in 0. And then we plug in negative 3. Okay, so I think this might be a little confusing, so just one step at a time. Subtract, then look at the inside. We have a negative, and then we're plugging in the negative 3 cubed for x. A lot of negative signs, so it can be a little, at least to me, a little confusing. So just be careful on that. But the first part here, everything is 0. The second part, to our minus, so let's just leave the minus out front. And what does the inside become? We got a negative, then a negative 3 cubed divided by 3 plus 16 times negative 3, and we get negative 39. Now remember, that is the inside, so it's not just minus 39, it's minus negative 39. And then the double minus becomes a plus, and we get our final answer of 39. All right, but one important thing, one way you can pretty much always check if you set it up wrong or not, is if you don't get a positive number here, it's not right. The area must be positive. Right, area cannot be negative. The definite integral can be negative, but when we set it up specifically to do the area, it must be positive. So if you solve one of these area problems in 6.1 and get a negative number, you're definitely wrong. Now you might only be wrong by a negative sign if you do these backwards, so you actually do bottom minus top. Like if I did these backwards, then I would actually come out with negative 39. So I'd only be off by a negative sign, but you need to fix it. Right, number 2. Same kind of question. We want to find the area between these two curves on the given interval. So we want to figure out which one's on top and which one's on bottom on this interval. And we're going to do the same thing as last time. We're going to plug in a number between, this time our interval is negative 2 and 1, to see which is on top. And luckily here 0 is between negative 2 and 1, so I'm going to plug in 0. So for the first one, we got y equals negative e to the 0. Now anything to the 0 is 1, so this is negative 1. The second one is just 0, like the last question. And coincidentally, the top belongs to 0 again, because 0 is bigger than negative 1. Okay. Now, of course, not always is the 0 going to be on the top. Just happened to be in these two examples. All right, but let's go ahead and set up our area equation. We integrate from -2 to 1. We do our top, which is 0, minus the bottom. Since there's no plus or minus here, it's just one term. I don't need a parentheses. Dx. Simplify the inside like I did last time. I always do that first with these. So we got the integral from -2 to 1. The double minus becomes a plus, and the 0 is nothing. So the inside is actually just e to the x dx. When we integrate e to the x, we get itself. So we integrate that. We have our evaluation bar from -2 to 1. Then we do the top, plug in the top, minus the bottom. We got e to the 1 minus e to the -2. Now this is a fine answer. You don't need to do anything with this. This is what we call the exact answer. If you want to plug it in your calculator to, at minimum, see that it's positive, go ahead and do that. But once again, read the directions as far as your answer goes. So we got e to the 1 minus e to the -2. And you do see that it's positive, so we definitely didn't plug them in backwards. And if you need to round, just round as far as it says, round 2.583, rounded to 3 spots. All right. But for the most part, when you find the area between two curves, that's it. Now there are examples of problems where you don't need to be given the endpoints because the way the graphs work is they intersect each other. And it just wants you to find the area between them where they intersect. So this last example we have here is exactly one like that. It says, it is not necessary to be given the intervals to find the area between two curves. In this case, we set the functions equal to each other to see where they meet, and these will form the interval. Now, I'm not going to use the graph in general to find the points of intersection, but I'm going to graph these two to show you what I'm referring to. It says find the area of the region enclosed by the curves y equals 3x squared and y equals 27. Notice that there are no given bounds, no given a and b. What we're going to do is set the equations equal to get the two x values. And they'll be a and b. But once again, I'm going to graph both of these just so you can see them. All right, so y equals 3x squared and 27. Now, because it's going to have to intersect at 27, I know that we're going to have to at least adjust our window to see 27. So maybe let's go from 0 to 30. So 27, actually that needs to be the y values. The x values, we'll just leave at -10 to 10 for now, the standard ones, and adjust if we need to. The y's, let's just start at 0. It's always a good idea when we're not sure. And we should only need to go up to 27. So let's do 30 to give ourselves a little extra room. I'm just making the scale 5 so there's not too many dashed lines on the side. And then graph. And you can actually see what it's referring to. What it wants us to do is find the area between these two curves. All right, we want to find the area between these two curves. So what you need to do, especially if you can't graph it, you need to find where they intersect by doing this, and then also figure out the top and bottom. Now, from our area picture here, you can kind of see which one's on the top. It's going to be the y equals 27. but we'll go through and do it all as if we didn't graph it in the calculator. All right, so first step is to find the bounds. All right, so when I say set them equal to each other, I mean just the part without y. So 3x squared equals 27. Solve this for x. We divide each side by 3. We get x squared equals 9. And then to go from x squared to x, we know to do the square root. Now we do have to get two numbers because it has to intersect in 2 points, and we see that in the graph. If it only intersected in 1 point, then our area wouldn't stop. It would be infinite. So it's going to have to be two numbers, and that's a real reminder that you need the plus or minus when you square root. So we get x equals plus or minus the square root of 9, which is 3. All right, so we figured out the bounds. It's from -3 to 3. If you want to write it like this, you can, like the other ones. If you want to fill it out like that. So we kind of filled that part out ourselves. But when you're not given this, you have to figure it out. This is the only way to figure it out. Right? Then we'll figure out which one's on top. And according to our picture, it should be the 27. We'll do the exact same thing as we did before. Plug in a number between -3 and 3. And because I have 0 there, I'm going to plug in 0. For the first one, if I plug in 0 for x, I get 3 times 0 squared, which is just 0. And the second one is 27, no matter what. So the y equals 27 is on the top, which it needs to be because of our picture. And then 3x squared is on the bottom. Right. Once again, don't just assume based on the problems that I have here that your top and bottom are going to always be the top is the number, the bottom is the thing with the x, because it can definitely be changed. So check that. Right. But now as soon as we figured out the bounds here, we're really at the other problem. We did our top and bottom. Now we set up our area integral. -3 to 3, our bounds on x. The top is 27 minus the bottom, which is 3x squared dx. And just like before, what I said, once you set up the integral, if you kind of get amnesia about what you were doing before, it's just a problem from 5.5, and we solved this. We can integrate each part. The integral of 27 is 27x. The integral of 3x squared, we would get x cubed over 3. But since we have the 3 on top, it actually just cancels out and gives you x cubed. Actually, let me go ahead and add the extra step just to be careful. And then we have our evaluation bar from -3 to 3. Okay. Now, the only thing to simplify, right, we didn't have to simplify at the beginning, which I should have mentioned inside the integral. The only thing I would simplify here is cancel those 3's out. So we got 27x minus x cubed from -3 to 3. And now I'm going to plug in the evaluations. So we're going to plug in 3. Subtract, and then plug in -3. And I didn't leave myself enough room. Let me write it on the line below. We got 27 times 3 minus 3 cubed minus, plug in -3, we got 27 times -3 minus -3 cubed. One thing, especially with these when the bounds are exactly negative of each other, it's pretty common to look at very quickly and see this and think everything's going to cancel. But just be careful, just do it out. You've done a lot of the work already. No reason to try to rush what I would consider the easiest part. So the front thing, we got 27 times 3 minus 3 raised to the third power is 54 minus, and then 27 times negative 3 minus negative 3 raised to the third power. That's negative 54. Now this very often happens that when it's symmetric like this, negative 3 to 3, if it was negative 7 to 7, this number and this number are the same but opposite. But once again, just don't look at the 54s and think they cancel, because we have a double minus, which becomes a plus here. And 54 plus 54 is 108. All right, so the area of that region is 108. I'll just show you the graph again. But this is a very odd shape. You wouldn't have a formula for it normally. And its area, somehow it works perfectly to be 108. Right, but that is area between two curves. And really what we're going to be doing in section 6.2, even though they're all word problems, in a roundabout way, it's going to be asking us to find the area between two curves. So we'll be doing a lot of similar stuff to this. It just won't say find the area between two curves then.